All right, so I'm Derek Gersman, and I'm going to be presenting our sketch on a performance-oriented data parallel virtual machine for GPUs, a system that we've been working on for quite a while. And actually, Mark Siegel and Mark Piercy originally spearheaded this effort at ATI, and I've been helping and working with them in terms of system integration and tool development for this particular abstraction layer. So what are we trying to solve here? Well, looking back at the various research efforts into since around 2002 when programmability was first introduced into the graphics hardware, the state of GPU programming hasn't really changed in close to 5 years. This has been presented numerous problems when trying to use the GPU for non-graphics-based calculations, as outlined by the description of the GPGPU course from last year's SIGGRAPH convention. So as the course organizers said, significant barriers still exist for the developer who wishes to use the inexpensive power of commodity graphics hardware, whether for in-game simulation of physics or for conventional computational science. These chips are designed for and driven by video game development. Thus, the programming model is unusual, the programming environment is tightly constrained, and the underlying architectures are largely secret. The GPU developer must be an expert in computer graphics and its computational idioms to make effective use of the hardware, and still pitfalls abound. I think this sort of summarizes a lot of the problems that a lot of the researchers have stated in their papers. So when do these problems start to become apparent? Well, when you start to use the GPU for a compute device. And due to the low-cost, high-performance, widespread availability, there's been a lot of interest in using the GPU for various compute applications. For example, linear algebra, physics, convolution, sorting, FFT, and rendering, in this case, final frame rendering, stuff that you would typically use with an offline renderer. And looking at all these applications, you can actually start to realize that most of these only exercise a small fraction of the features in the graphics hardware, which we started to look at in terms of developing a new abstraction layer. So the current GPU abstraction is actually just the rendering pipeline. So developers are still forced to use OpenGL and Direct3D for communicating with the graphics card. So as a result, they impose graphics-centric programming model, which forces the application to manage graphics state, even for non-visual computation. Furthermore, the APIs are poorly correlated to the underlying graphics hardware. They're implemented through a graphics driver, which is designed to hide the hardware resources. And due to the high-level interface of these APIs, the driver is free to impose critical policy decisions, especially for how, when, and where data resides. And because GPUs are driven by the gaming industry, these policy decisions are optimized for graphics and games, and may actually impair performance for compute. Finally, an updated graphics driver can actually exhibit drastically different performance as various optimizations for games and features get added. And clearly this model seems less than ideal when you're actually trying to do compute and want to guarantee some sort of application performance. So what we're presenting here is an alternative model, one that takes a data parallel approach, which we describe as the data parallel virtual machine. Unlike graphics APIs, this approach exposes the hardware and the relevant parts of the GPU as they really are. So the interface is provided through three major components: the command processor, the data parallel processor arrays, the memory controller, and basically everything that's non-essential in terms of graphics features, we actually just hide because they're not all that relevant for doing compute. As a result, we're able to expose low-level communication to the device and provide direct interfaces that deal strictly with, actually accessing the hardware resources. And plus, on top of that, we'd like to eliminate the driver-implemented procedural API and really drive policy decisions back to the application. This also would remove all of the overhead of a typical driver that has to implement a graphics API and maintain internal complex state for the various graphics API calls. So here's a simplified block diagram of the data parallel virtual machine. The application interfaces with the DPM through a single shared object, or DLL in this case, there's basically 4 methods that can be invoked. One, to open a connection, which returns a structure that contains memory handles to all the resources available on the graphics card. And then you can also close the connection, submit a command buffer, and then there's also a synchronization call to wait for that command buffer to be consumed. And as you can see here, the 3 major components are the command processor, the data parallel processor array, and the memory controller. The application also has access to all the memory resources on the card, including GPU local memory, which only the graphics hardware can read and write to, as well as host memory, or PCIe Express shared memory, which the application and the graphics card can read and write to. So in this sense, the application submits all of its data through the shared memory or the host memory, and then the graphics card can either use that for inputs, outputs, or results. And also in our model, memory is just memory, so instructions and commands and constants, inputs and outputs all get stored in all of these memory pools. So looking at the DPVM in more detail, the first major component is the command processor, and it abstracts the communication from the underlying architecture. So commands are architecturally independent, and in this sense, the command processor actually interprets all of those commands and submits them to the processor array. So the command buffers, as I said previously, are actually stored in memory, and the work that's necessary for the processor array is distributed through the command processor. But the main thing here is that the application manages packing and filling command buffers and also submitting them to the command processor. And the application also handles synchronization using that 4th method that I mentioned within the data parallel virtual machine shared object. So the application handles all synchronization on the device. And here's a complete list of all the data parallel commands that we're supporting. So you got commands for program execution in terms of setting up your execution domain, where your program addresses are, commands for starting your programs, as well as setting output masks. And then there's also conditional values that can be set, which in terms of graphics would be more like def test or early Z, so that you can break out of your program execution early. You also have controls for validating and invalidating your cache. So the application explicitly controls cache invalidation. So in this sense, this includes instructions and constants, as well as inputs and outputs. And the conditionals, which are the conned out, are again tied to the early Z testing. We also provide explicit control over the memory layout in terms of the formats and locations. The application actually specifies where, where all the memory resources are located and their formats. And finally, we provide access to the performance counters, which are actually hardware registers which contain information for real-time profiling. So you can init the performance counters, start and stop, and then read the values. The second major component is the data parallel processors, which perform the floating point computations. So one thing that I should probably mention here is that we're only interested really in floating point. So all of the memory formats that we expose currently are just float 32s. So you're allowed to do single, dual, or 4 component float formats, and I'll get into more detail on that later. But another major thing that we've added here is we've come up with a formal application binary interface. And in this sense, we've used the standard ELF format, which is one that's been adopted by many Unix operating systems, including Linux. It's basically just a very structured format for specifying a binary executable. However, in the text section, which contains the actual instructions, we're using the native instruction set architecture of the processors. So just like you would code to the x86 ISA, you can code to the x1K ISA. So the ISA is obviously architecturally dependent, but in our DPVM model, only the ISA needs to be updated for new architectures. So what this really means is just recompiling your programs, but all your program logic remains the same. So the commands that you're submitting through your command buffers don't need to be modified. And finally, the application submits the compiled binary, and because it is binary, the executable is immune to driver changes. So the third major component is the memory controller, and it services the GPU request to read and write memory. And since we export the graphics memory directly, you get handles to GPU memory, which I mentioned earlier as being accessible only by the GPU, as well as the host shared memory, which is accessible by the CPU and GPU. And you actually get the memory addresses, and your application can manage all the memory allocation in terms of what is available within those memory pools. So you can specify the locations and formats, and you can also cache between formats without doing an additional copy. And finally, the application also controls the caching validation, so you can say explicitly when caches should be updated. So initially, our implementation right now is on the X1K architecture, and marketing is trying to work towards productizing this, and the name that they've chosen is CTM, which stands for close to the metal. This is our device interface layer. So the Radeon X1K architecture, one of the major cards is the X1900, has greater than shader model 3.0 resources, and we expose all of these. So as I mentioned earlier, the DPVM model adopts a native ISA, and we provide both text and binary formats for this. Our implementation has a single runtime library, which just uses a lot of our low-level driver components. And then we've also been developing several support libraries for doing such things as command buffer packing, memory allocation, and then we've also got an assembler disassembler to the hardware ISA. So as far as our processor resources on the ATI Radeon X1900, you've got 16 inputs, which would be normally textures of float 1, 2, and 4 components, as well as 4 outputs, which would typically be multiple render targets, again of the float 1, 2, or 4 formats, and these have an assigned XY output location. Or for outputs, you also have another operating mode, which gives you unlimited outputs, but it's restricted to a single floating point component, but allows you to have an arbitrary XY output location. You also have 512 instruction slots, which can be any combination of ALU, flow control, input, or output. So with dynamic flow control, this actually gives you a lot of flexibility, especially when you combine it with dynamic branching. Finally, you also have all of the constant stores. So you've got 256 float 4 constants, 32 integer constants, which can be used for loop control, as well as Boolean constants for doing conditionals, and 128 general purpose registers of float 4, which is, again, greater than shader model 3.0, and also the 256 float constants is greater than shader model 3.0. And if I was too subtle, the infinite outputs allows you to do scatter, which is something that no high-level API has actually integrated into either a high-level language or exposed through a method call. So again, additional features beyond shader model 3.0 and stuff that isn't available in any graphics API since it hasn't been adopted by any spec is scatter, which allows you to output float 1 formats or float 1 values to arbitrary locations, as well as tiled memory formats, which are a high-speed optimal format which our memory controller is optimized for. And one in particular is fetch 4, which allows you to retrieve 4 floating point 32-bit values in a single clock, which for some applications can actually increase your bandwidth by 4. You also have the ability to read and write directly to and from host memory without an additional copy. So the PCIe Express does the transaction directly to system host memory. And you can also avoid non-IEEE floating point optimizations. So nans and ints can actually be given the correct behavior using this abstraction layer, since you do have direct device interaction. The application also is able to dictate the granularity of the command buffer submission, and ultimately this gives you an unlimited application execution time. So you can pack your command buffer with multiple program calls of any number of shaders, and so you can actually just run an entire complex program on the graphics card without any restrictions, more or less. So I'm going to jump into some demos real quick. So we've been working with a number, a number of partners, including Stanford, and what I'm going to be showcasing here is their next generation GPU-based ray tracer. So the system that I'm running on is got two X1900 graphics cards, both as separate discrete devices. So they're not interconnected, but we're communicating and batch processing across both cards. And they've got a tiled rendering algorithm so that tiles get distributed across both devices. Sorry. Too many keyboards. So this is one particular kitchen scene. They're actually doing two reflection bounces as well as doing a diffuse reflection model underneath. And it's adjustable, so you can turn off the reflected rays and increase performance or increase the number of bounced rays to give you more reflections. So this is running at 512 by 512, and it's tunable in terms of the number of rays that get cast. And another thing that I should mention here is that they're doing a stackless KD tree traversal. So for internal environments, this gives you a very optimal ray traversal acceleration data structure. And this is, again, an improvement upon the 2005 Foley paper that was presented at Graphics Hardware by Stanford. So this is just another scene. This one actually, let me just, so this particular scene actually contains upwards of 70,000 polygons. It's got some complex models, in this case robots. But this scene actually contains several city blocks worth of data. So this is just the diffuse intersection path. And then, again, you can add multiple bounced rays. So this is another application that I ported over. This is a Quaternion Joy set that's being ray traced. So this is actually a port of Keenan Crane's original GPU-based solution that was running through OpenGL that we ported over to the DPVM layer. And again, we're processing across two different cards. So this is an implicit surface, so it's completely being determined by intersection points. They're all calculated by evaluating a complex polynomial equation with multiple iterations. And this is actually just a slightly different version. In this case, I'm actually calculating two samples per pixel and then jittering them to get slightly better features at particular edge locations. And the main thing here is that we're doing twice the amount of work, but our frame rate is only dropped by like 5 to 10 frames a second, depending on which random offset we're actually using for the features that are being generated. So looking at some of the applications that we've ported over to the DPVM and comparing on the same architecture, running through the two different abstraction layers that are available to us, either OpenGL or the DPVM, we've outlined sort of the overall benefit in terms of performance. So one particular application is matrix-matrix multiply, which in this case we've got a 10x benefit in terms of performance simply by using and adopting several of the DPVM features, including specific command buffers that we're submitting, being able to hand code to the ISA for additional optimizations. In particularly, we're using specific memory formats for tiled memory, which give us very fast bandwidth. And we're also modifying the memory offsets to avoid running into situations where we're accessing memory from the same bank, which can degrade overall memory access. We're also interleaving multiple passes to take advantage of the number of ALUs that we have, and we're using fetch4 to increase our bandwidth by a factor of 4 for texture inputs. Another application is FFT, where, again, just porting it over, we're getting a 2x performance benefit by packing a specific command buffer, being able to hand code to the ISA, and then interleaving multiple passes. And then the two applications that I just showed, which were the Stanford GPU ray tracer and the Quaternion Julia set implicit ray tracer, were just ported over. There's no actual optimizations that we've looked into yet. And the main benefit is just being able to pack a specific command buffer and having total control over the memory formats and the memory layout, which immediately gives us a 2x performance benefit. So in conclusion, some of the benefits of the data parallel approach that we're providing here are a straightforward programming model. It allows you to have hand-tuned optimizations, which you wouldn't get running through a typical high-level language. It also exposes the actual hardware device, so you have direct control over the memory and the processors, and the application binary interface and native ISA give you the ability to do hand-coded optimizations, as well as being able to compile from a higher-level language. And again, this is the only component of the DPVM which is architecturally specific, so in the future, all your programs will only need to be recompiled, but the rest of your application logic remains the same. And finally, the application is responsible for all the policy decisions which would normally be governed by a graphics driver. So ultimately, this allows you to have consistent performance for compute, so you can guarantee that your application will be running within a specific amount of time. So in terms of future work, other things that we're looking to explore, by exposing a lot of the graphics hardware device resources, it really opens up the area for tool development, especially debuggers, which is something that the industry has been really looking for, as well as statistical runtime profilers at the hardware ISA level. I think that would be a great thing to look into in the future. It also opens up a wide realm of opportunities for compiler research in terms of data parallel high-level languages and non-graphics optimizations. So I just wanted to thank ATI Research, especially Mark Piercy, Mark Siegel, Alpana Colgood, and Raja Kaduri, and everybody else that's been helping us, as well as the people that we've been working with at Stanford University, Mike Houston, Daniel Horn. And finally, if anybody has any questions, and also I should mention at this point that we're very interested in working with researchers and universities. So if you have any questions or you have any projects which you think might benefit from this abstraction layer, by all means contact us at researcher@ati.com.